If you live almost anywhere in the United States, you've gotten the text. It shows up on the hottest afternoon of the year. Please reduce your electricity use between 4 and 9 p.m. Set your thermostat higher. Hold off on the dishwasher. Stop and think about how strange that is. The most advanced power grid on Earth, on the one day it's needed most, has to ask you, politely, to please use less. The obvious explanation is that too many people are running their air conditioners. That's part of it, but it's only half the story. Because a heat wave doesn't just push demand up. It attacks the grid from two directions at once. Here's the first thing to understand about the grid. It isn't built for how much electricity you use on an average day. It's built for the single hottest hour of the entire year. That moment, the annual peak, is the number every grid planner designs around. There has to be enough generation, enough transmission, enough of everything to serve demand at its absolute maximum, or the lights go out. Which means most of the year, a large chunk of that capacity is just sitting there, idle, waiting for the worst day. And the worst day is almost always a summer afternoon. PJM, the grid operator for the Mid-Atlantic and part of the Midwest, the largest in the country, forecast a record summer peak of around 166 gigawatts for early July of 2026. That edged out its previous all-time record, set back in 2006. A gigawatt is a billion watts. 166 of them is a genuinely staggering amount of power, all being demanded in the same handful of hours. And nothing on the calendar drives demand toward that ceiling faster than a heat wave. When it's 100 degrees out, the grid climbs toward the very top of what it was ever built to deliver, and it does it in a matter of hours. So why is heat, specifically, such a problem? Why does a hot day spike demand more than a cold one, or a busy one? It comes down to air conditioning, and one property that makes it uniquely hard on the grid. It's correlated. When it gets hot, it doesn't get hot for one house. It gets hot for an entire region at the same time. Millions of air conditioners, in homes, offices, stores, warehouses, all switch on and start cycling in the same hours, for the same reason. There's no averaging out. Everyone's peak lands together. And unlike most of what draws power, air conditioning load tracks temperature almost in a straight line. Every degree hotter, and those compressors run longer and harder. Across a whole region, each additional degree can add gigawatts of demand, the output of entire power plants, just to hold everyone's indoor temperature steady. There's one more twist. This AC demand doesn't peak at noon, when the sun is highest. It peaks in the late afternoon and into the early evening. Heat that built up all day, people arriving home and turning things on. And that's the exact window when solar generation is starting to fade for the day. Demand is climbing toward its highest point right as one of your supply sources is walking off the field. That's the half everyone already sort of knows. More heat, more AC, more demand. Here's the half almost nobody thinks about. The same heat that drives demand up quietly makes the grid worse at delivering power. 3 separate mechanisms, all pulling the wrong way at the same time. First, the power plants themselves. A gas turbine, the workhorse for meeting summer peaks, is essentially a fixed volume machine. It pulls in a fixed volume of air, compresses it, and burns fuel in it. But hot air is less dense than cool air. Less mass of air per breath means less oxygen to burn, which means less power out. As a rough rule, a gas turbine loses somewhere around 5 to 10% of its rated output for every 10 degrees Celsius the air rises above its design point. On a brutally hot afternoon, a plant simply cannot make the power its nameplate says it can. Second, the transmission lines. Those big overhead conductors carry a limited amount of current, and that limit isn't fixed. It depends on how fast the line can shed heat into the surrounding air. On a hot, still day, the air can't cool the line as well, so the conductor runs hotter for the same current. Push too far and it sags, literally droops closer to the ground, toward its safety clearance limit. So on exactly the day you most want to move power around, operators have to allow less of it through the wires. Third, the transformers. Those substation units dump their waste heat into the ambient air too. When that air is 100 degrees, they have far less cooling headroom. You can safely load them less, and running them hard in that heat ages their insulation faster. Added up, the plants make less, the lines carry less, the transformers hold less. Deliverable supply shrinks at the precise moment demand hits its annual maximum. Now put the two halves in the same frame. Demand at the highest point on the calendar. Deliverable supply pushed below what the nameplates promise. The grid is being squeezed from both ends simultaneously. The space left between them has a name: the reserve margin. It's the buffer, the cushion of extra supply above expected demand that keeps a single tripped plant or a surprise heat spike from turning into an outage. On a mild day, that margin is comfortable. In a severe, wide-area heat wave, it can shrink to almost nothing. This isn't a hypothetical. NERC, the body that assesses grid reliability for North America, named long-duration, wide-area heat as one of the primary reliability risks for the summer of 2026, right alongside generator outages and fuel supply problems. The grid added something like 58 gigawatts of new resources over the prior year, which helps. But aggregate peak demand keeps climbing, up more than 11 gigawatts year over year, and data center load alone is projected to jump from around 44 to 55 gigawatts. The ceiling isn't holding still, it's rising. This is the reason summer, not winter, is the classic danger season for most of the US grid. Winter has its own risks, but summer is when demand and the weakness of the hardware peak in the very same hours. Which finally explains that text message. When the reserve margin gets thin, an operator's options narrow fast. Every available plant is already running flat out. Imports from neighboring regions are already maxed. The transmission lines are already at their hot weather limits. There is no big hidden reserve of power to switch on. That's the whole point of a peak. So the cheapest, fastest, safest lever left isn't on the supply side at all. It's demand. If everyone shaves a little, nudges the thermostat up a couple degrees, delays the laundry, you can knock a few percent off the peak. And a few percent, right at the top, can be the difference between staying on the edge and going over it. That's what the conserve-energy alert actually is. It's not public relations, and it's not the grid being fragile for no reason. It's called demand response, and it is a deliberate, planned tool. The last soft buffer the operator reaches for before the only remaining option is the hard one, deliberately cutting power to some customers, in rotation, to save the system as a whole. Controlled rolling blackouts. The text is the step that exists specifically so it doesn't come to that. Here's the part that doesn't resolve. That ceiling, the annual peak the whole grid is built to chase, keeps climbing. Data centers don't cycle off in a heat wave the way a home thermostat does. And each year, the hottest hour tends to arrive a little hotter and a little hungrier than the last. Where that peak lands a few summers from now, and whether deliverable supply keeps pace with it on the days that matter most, is a question the grid has not answered yet.